So hi everyone. I hope that you're going to enjoy the reading group talk today. So our focus today is going to be on specifically on machine learning techniques and data for stock market forecasting. And the article that we're looking at today is by Mahendra Kumbere and other authors. So that is our focus for today. So what we're going to be looking at is we're going to be looking at this landscape of stock market predictions that have been examined in literature. And our main focus will be on this literature review in this article that was conducted by various research studies, specifically in machine learning for the prediction of stock returns. So our goal today will look at this maze of research and get this general overview as well as this holistic idea of different machine learning techniques that they are available in stock market predictions. And we're not going to go in depth with each technique, but at the end of today's talk, you're going to have a good idea and a good overview of the different types of techniques as well as approaches that there are available in order to predict your stock returns. So looking at this efficient market hypothesis, and how does machine learning techniques then also come into the picture? So let's see. So in 1960, Eugene Farmer introduced this idea of the efficient market hypothesis. And the idea behind this idea was that when there's public available information, it will be incorporated into your price of stocks. So everything will be priced in. And there are different types of efficient market hypothesis available. For example, the one is the semi-strong form efficiency. And what that's telling us is it's related to that idea of how the stock price will always adjust instantly when there's that new public information available. And that also goes along with our random walk theory, because when we have these sudden price movements, that could definitely be a result of that new information entering the market, and it will then cause these traders to react in this random fashion that we see in this illustration. So how do we then bring machine learning techniques into this picture? So with efficient market hypothesis, we know that when traders quickly act on these different patterns using this historical data, that opportunity of trying to outperform will definitely get less. So this is now when machine learning techniques come into the picture in order to bring the stock returns and bring us this new opportunity to outperform the market. So we'll be looking at these different machine learning techniques today, as well as have a review of the technical aspects that we can add to these machine learning algorithms in order to help us to predict these stock returns. So just as a side note, today our main focus is going to be on the non-linear machine learning models. So we're not going to start off with the linear machine learning models, such as linear regression. So we're going to assume that everyone's familiar with these linear machine learning techniques and algorithms, and we're going to jump straight into the models that are mainly focusing on non-linear approaches. So the models that we'll focus on is that of deep learning, support vector machines, neural network, as well as fuzzy logic. So today's focus again is going to be on stock return predictions and how we can do that with these machine learning techniques. And just as a general overview, why it's so important for us to look at these stock return predictions is there's many reasons why it's very important. And one very important reason is that of informed investment decisions, because it's identifying those potential opportunities for generating returns as well as avoiding your losses. And the two main approaches with stock return predictions is to predict the stock returns with regression. And that's when we have that predicted value, which will represent our expected change in the stock price. And the second approach will then be classification in stock return predictions. And that's where we categorize that potential movement of the stock in different classes. So these stock returns predictions can then also be made over different time horizons as well. So in this article, what it's looking at is they went and classified the different categories into regression, classification, and clustering. And the main type that the article specifically looks at is that of the regression type machine learning technique. And why it's so important to take note of why this regression is the main type is it's suggesting that it's a very significant area of study. So this emphasizes how relevant it is, in our real world application when we predict stock returns. So in this literature review, what they did is they looked at 138 different journal articles between 2000 and 2019, and to keep it relevant. And then they looked at how these different articles within machine learning used to predict returns. And we'll have a look at a few of these. So when we think about general classification problems, is there a specific machine learning tool that can help us in order for us to split our data into different categories? So let's have a look. So our first machine learning algorithm that we're going to be looking at is that of support vector machines. And what support vector machines is specifically doing is it's specifically for classification tasks. So what it does is it finds this plane or line, depending on our dimension that we have. And then that plane or line will then act as that boundary point in order to split our data into categories. So over here, we can see that we have the blue category and the orange category that this line or hyperplane has split our data into. And then what we can also see from the sketch on the right is that this margin that we see over here, what it's representing is that's that distance between our hyperplane or our line and the distance between the nearest data point in each class that we have. So what that margin's then representing at the end of the day is it's showing that confidence in our model's prediction. And when we have an optimal hyperplane is when that margin that we have is maximized. And one reason why our model will be optimal when that margin is maximized is the reason of generalization. So that larger margin will then indicate that better generalization capability, and that maximum margin will then help that data perform better when we work with unseen data. So we're going to be looking at a few of these support vector machine combinations and what can we add to support vector machines in combination with it in order to get the most out of our predictions at the end of the day. So the first combination that we're going to be looking at is that of PCA. So they use principal component analysis, and then they use the weightings for our support vector machines as well. And the main reason why they look at weighting specifically for our support vector machine is because they want to take into account that imbalance that could occur when we have our two categories or our categories in our data. And when we add these weightings, this weighting scheme in this support vector machine, is we'll then get these different weights for our data points based on how important we think they are. And this will then help us to emphasize, more importance in different categories. And that's very useful, especially when we have this imbalanced data that we see over here, for example. And then what will happen when we weigh and balance this is our support vector machine will then learn from each category. It will get a chance to learn from each category a little bit better now because of this balance that's occurring. But it is important to note when we do create those weights and those balances for our data, we need to know the specific problem that we're dealing with and the specific situation, and how, certain imbalance ratios will work better in our situation and scenario than others. So what this principal component analysis then does is it will then reduce that computational complexity that we find, because of, it's doing that dimensionality reduction that we find in PCA. And then overall, when we look at PCA as well as the weightings in our SVM, it's helping us and improving the SVM where we have imbalance between our categories. And then it's helping us if there's a high dimensionality challenges that we face with the PCA. And then another technique that also combines our support vector machine that we can use before this is called particle swarm optimization. And the idea behind this PSO is it was inspired by the social behavior that we find when we see birds or fish, and that behavior where they swarm in nature. And then that behavior is put in place over here. So what this particle swarm optimization's goal is it's trying to use this optimization in order to find your optimal solution at the end of the day. And the way that it goes about doing that is it goes and searches through this multi-dimensional space, and then it creates this population of potential solutions that will basically swarm through the solution space, and then they'll find this best combination that they find with the hyperparameters. And then once I have this optimized hyperparameters, they'll then go further and they'll use that then in our support vector machine algorithm further on. So another optimization technique that we can also use alongside the support vector machine is that of this teaching learning-based optimization. And the main goal behind this teaching learning-based optimization is it's inspired by this teaching and learning process that we observe in a classroom, for example. And the core concept behind it is it's trying to take that teaching and learning observation that you can see in a classroom, and then it's updating that knowledge of our solutions in our population. So it's simulating that teaching process, and how it does that is it takes our better solutions, which are then called the teachers, and then those better solutions will then guide those solutions with less quality, so our learners in our population. And then that knowledge transfer that's occurring between our better solutions and our solutions with less quality, that's then enhancing our overall population performance through these iterations that take place. And then once we have this from the teaching learning based optimization, once that's done, we then have our optimized parameters or our optimized features. And then that will then further on get used in our support vector machine from there. Another component that we can look at with support vector machine is what it does. It's independent component analysis, and it's specifically used when we pre-process our financial data, so our input data. And what we want to do, the goal from this, is that we want to extract independent components. So what it specifically does is it takes mixed data. So our input data will definitely be mixed. And then it goes and separates these factors from our input data from the noise. And from there, we then get these independent components that we can choose which independent components do we want to add to our input data to get the best forecast out of it. And then once these independent components are extracted, we use that then for our input features in our support vector machine from there. So I'm sure a lot of you are familiar with principal component analysis. So let's quickly just have a look at what is the main difference between this independent component analysis that we just had a look at and principal component analysis, just to get that overall understanding of the difference between these two specifically. So when you look at this independent component analysis and principal component analysis, let's look at an analogy of a burger. And let's say we want to analyze, the different components that we have in this burger. So when we look at independent component analysis that we just saw previously, we'll identify using independent component analysis and looking at this burger. We'll then identify these individual ingredients that the burger has. And how we do that is we separate these components from each other. So we'll identify, for example, the patty, the cheese, the tomato. But when we look at principal component analysis, here's where the difference comes in. We'll look at, this dominant flavor of the burger, for example, and we'll take that dominant flavor and we'll try and reduce that complexity. And that's the reason for that is we want to focus on that important components in the burger. So that's a main difference between ICA and PCA in this burger analogy, just so that you can understand the difference between the two. And now a question that we'll get is, how do we handle imprecision? Because our main focus now with support vector machine learning was looking at that precise classification. And now let's shift our focus from that precise classification that we saw in support vector machine learning, and let's look at more uncertain situations, and let's see how fuzzy logic will handle these uncertain situations that we do find in data. So let's just get this general overview of fuzzy logic for those of you aren't familiar with what it means. So we all know what Boolean logic means. Here's a quick overview of Boolean logic and an example of it. So if we're looking at, let's say, a return of 1.5%, and let's say there's now these classifications, it can either be higher than 1%, it can be between -1 and 1%, and then it can be lower than -1%. When we use this Boolean logic, there's either a yes or no, a 0 or 1. There's no sliding scale between the 0 and 1. It's definitely in a category or it's not in a category. But when you look at fuzzy logic, where this difference comes in is we can have the sliding scale between 0 and 1. So the sliding scale between yes and no. And in this example, let's say we're looking again at this return of 1.5%. And now we're saying, is this return higher or is it 1% or higher? Now you can go and assign, let's say, 70% to that. Yes, there's a 70% chance of it being, higher than 1%, instead of saying definitely yes or definitely no. So it's allowing for those uncertain situations that we can find in market predictions. So it allows us to use that sliding scale between our 0 and 1 instead of just putting something in a category immediately. So looking at different types of fuzzy theory and different ways that we can apply fuzzy theory. The first fuzzy theory model that we'll look at is that of ANFIS. And that was developed in 2009 when there was research done on that. And what they looked at for this ANFIS model, so it's that adaptive network-based fuzzy inference system, is they wanted to capture these patterns that we find in the stock market. And they specifically wanted to use these fuzzy logic rules in order to capture these patterns. And how they did that is they also used neural network learning together with fuzzy logic. And we'll have a quick look at neural networks after this as well. And what this system did is there were two main phases in the system when they developed it. So the first phase was the control phase, and all it specifically did is it was capturing these patterns that was found in our input data, and those patterns were captured with these fuzzy logic rules. And then secondly, what it looked at, the second phase in this model, was the predicted phase. And they then used neural networks in order to predict these certain trends that we find in our stock market. So they use the neural network to then predict the returns in our stock. So how can we then use this fuzzy theory if let's say we have input data and our input data has a bit of uncertainty, or our input data has incomplete information? What do we do using fuzzy theory in order to help this incomplete input data that we have? So one specific system that helps this is called the fuzzy gray system. And what it's specifically dealing with is that, that fact that if we have incomplete data, we use this fuzzy gray system. And what they do is there's two systems that they use. They first look at gray theory. So that's the first thing they look at is gray theory. And what it does is gray theory is a model that specifically looks at that limited or missing or uncertain historical data. And what it does is it then estimates your system's behavior based on the available data points that we have. So it specifically looks at that. And then what this fuzzy gray system is it's combining our gray theory, and then it's also combining our fuzzification. So fuzzification is when we capture that uncertainty in our stock market. And when we capture that uncertainty with fuzzy logic in our input data, that then gets applied into this gray theory to make these predictions that are a bit vague or limited based on the limited data points that we have. It then takes that and it still makes a prediction for stock market returns. And then another technique that people look at is fuzzy time series. So what specifically happens with fuzzy time series is it's mapping our raw time series data, so our input data points that we have, such as, the stock prices that we have as input. And then it mapped those data points that we have, and it's mapping it then to our corresponding fuzzy sets. And this one will then capture the uncertainty that we have in data. And an example is, let's say we have a stock and it has a 5% increase in the last week. And let's say we can then use that 5% stock increase, and we can then assign membership to it. So we can say, okay, let's put 80% membership in the fact that the stock is rising. And that's then one fuzzy set trend direction that we can assign it to. And then we can say, let's put 20% of this 5% increase into a falling set. If there's a bit of uncertainty, whether is it really rising or is it possibly falling? And then from there, what we do once we mapped these time series data points to our fuzzy sets is it then goes into a rule generation where these fuzzy rules will then be generated on these patterns that we observed in our data. And then these fuzzy rules will then produce our fuzzy forecast. But then once we have this fuzzy forecast, we then go through this process called defuzzification. So it's taking these fuzzy forecasts and then it's producing numerical forecast values from that. So then we can use those numerical forecast values further once this prediction has been made. And then another interesting fuzzy logic technique that we can use is that of our fuzzy metagraph. So what this approach is doing is it's specifically there to look at issues of non-stationarity that we typically find in our financial time series. And what it's doing is it's applying fuzzy logic. And then after that, we construct this metagraph where each node in this metagraph will then represent different interests. For example, one node could specifically represent a particular stock, and another node could represent a market index. And the main differences between this metagraph that we found now in this fuzzy metagraph and a traditional graph that we find is when we look at a traditional graph, we might look at two companies, such as, let's say, Apple and Microsoft. And we'll look at how these two companies are correlated. Whereas when we look at a metagraph specifically, what the main purpose behind it is it could go and encapsulate this information from example, let's say we take the information from Apple, Microsoft, NASDAQ index, as well as news indicators. And now when we look at this traditional graph, you'll see that the focus will be mainly on first order interactions. So we'll draw these direct connections between our pairs of nodes that we have. But what makes this metagraph so special is it's encapsulating this higher order interactions that we find, and where we'll look at these relationships between two nodes that might also be influenced by surrounding nodes. So it's taking more context around it as well. And now looking at a different machine learning algorithm. And this machine learning algorithm is specifically good at looking at advanced pattern recognition. And the machine learning algorithm that we'll look at specifically now is networks, as well as deep neural networks. And we'll see how they're so good at pattern recognition. So neural networks is this machine learning algorithm. And what it's specifically used for, as we said, is it's specifically used for pattern recognition. And what a neural network does, the crux behind it, is these neurons will decide if they should activate or not based on the input that they receive. And these neurons are then organized in 3 different layers. So we see the input layer, the hidden layer, and the output layer. And what this input layer is doing is it's taking all your historical stock prices as your input. And then in this hidden layer, that's where all the process of the data will take place. And that's where it will learn to recognize certain patterns from our data as the input. And then this output will be where the prediction of these stock prices will take place. And then when we look at this neural network and looking at the neurons, we see that these neurons are connected by these weights. And these weights that are representing by the arrows, the weights are representing the strengths of these connections between our neurons. And as this network will learn the weights and adjust the weights, the goal at the end of the day is to optimize these weights in order to get our most accurate prediction that we could possibly get. And during the training process of this neural network, we'll have our input data available, and we'll also have our target values available as well. And then these weights will then be optimized iteratively until at the end of the day, we have the smallest difference between that predicted output that we have and our actual target value. And once we have the smallest difference, that will then be our optimal weights in our system. So we'll again look at different combinations that we find within neural network. And the first combination that we'll look at is what happens when we add a genetic algorithm to a neural network and see how that combination works. So let's just have an overview of what is a genetic algorithm and how does it work. So the main idea behind a genetic algorithm is it's inspired by the idea of that survival of the fittest. And looking at this illustration, what we start off with is we start off with a generation. So a generation is when we have a possible a population with possible solutions. So each orange circle here will represent our population with. And then we also have this binary string per population. And so our string is ones and zeros. And so 1 will mean it will get selected and 0, it will not. And we'll see how we can add values to these ones and zeros depending on our scenario. So from this generation then, we'll select the best populations from there and then go forward from there with that whole survival of the fittest idea behind it. So once then we choose our best populations from our generation, we then perform a crossover. So what happens is we have our, let's say over here, we have our 2 best populations, and then we decide the end strings will then switch in order to produce 2 more populations that will be optimal. From there, then we'll just bring a bit of diversity in. So we'll switch a few ones and zeros just to bring that diversity in. And then this process will continue until either we have already a set of number of generations that will continue on, or until there's a specific termination condition that we already have in mind. And how we use this genetic algorithm specifically now with our neural network. For example, we could say that our ones and zeros over here are representing parameter values or features. So we can decide, okay, yes, we are selecting these features, or no, we're not selecting these features. And then from there, go forward, and then we take that into our neural network after the genetic algorithm will then help us decide which features are the best to take forward or not. And then the second combination with our neural network is that of time series. And why it's so important to look at time series, and they specifically look at the gauge model. And the reason why they look at the gauge model alongside the neural network is the fact that this gauge model is specifically capturing our time varying volatility that takes place in our financial time series data. And our neural network doesn't always effectively capture our volatility. So once we then have this time varying volatility that the gauge model captures, we can then use this ensemble, we can use a ensemble model. And what the ensemble model will then do is it will incorporate that volatility estimates that we get from our gauge model, and it will incorporate that into our neural network predictions then. And why this is so valuable is that can help us to make better risk-aware predictions then at the end of the day when we add these volatility estimates into our neural network as well. And then another combination is that of neural networks, and then they add principal component analysis as well as STEM, so that's our stochastic time efficient neural network. And the process that this follows is they first use principal component analysis. So that will then reduce our dimension of that input data that we have using PCA. And then we use that from our input data that we have now, reduce the dimension. That will then become an input layer into our STEN. So that's then the input layer for our STEN. And then in STEN's hidden layer specifically, what happens is the neurons in STEN, they specifically have a stochastic activation function in these neurons. And the reason why they added this stochastic function in these neurons is that they wanted to mimic this random behavior that we see in financial markets. So adding the stochastic activation function in these neurons will help us observe these random behavior that we see in financial markets better. And then another thing that STEN has that's a bit different from an average neural network is it has a time effective function. So what that function specifically does is it modifies our weights of our neurons in these hidden layers. So this network will then be responsible for different temporal changes that occur. So that's that time effective function that's also added in our STEN, so that it's a little bit different from just the average neural network. And then a major problem that we face when we use neural networks is we don't always understand how the model will arrive at a specific prediction. So how we can go about understanding how our neural network came to a specific prediction is we can use a glare extraction model. So that's our genetic learning for accuracy-based rule extraction. And what it specifically does is it's there to extract these rules that will help us to interpret what this neural network specifically did in order to get to your final prediction at the end of the day. So it's there to provide us with this decision-making process that the neural network did in order to get to the final prediction. And then just looking at the difference between glare and SHAP, because I think people are more familiar with SHAP than with glare. It's very similar, but there are a few differences. So what glare specifically does is, as we said, it's there to extract those rules. And then from there, we can see what decisions did this neural network take in order to get to that final prediction at the end of the day. Whereas when we look at SHAP, what it's doing is it's telling us how much emphasis was placed on each feature. And if we know how much emphasis was placed on each feature, then we can get a bit of a better idea behind how it got to the final prediction. So one example could be, for example, if there was a lot of emphasis on interest rates being a macroeconomic factor, if we know that there was a lot of emphasis placed on this, that can then help us gain more insight into how it got to the final prediction and why. So now that we know about neural networks and the different techniques behind it, let's have a look at deep neural networks. So it's the same as neural networks. It's just the fact that there's more hidden layers added to the neural network. So the deep neural network, also known as deep learning, is looking at all these different layers in this neural network that's responsible for extracting these features from the input data. And it's important to note when we add these extra hidden layers to our neural network, we need to know the complexity behind our task and our project. So, and we also need to know the amount of data that we have available. So it's important to take all of those aspects into consideration before we just add extra hidden layers to our neural network. And then we'll also look at a few combinations of what we can add or combine with neural networks in order to get that optimal prediction of the returns at the end of the day. So if we take our neural network and we use our historical stock price data, but now if we also use our news data, what will happen when we do that? So what they specifically do here is they'll combine our historical data with our financial news data. And the way that they go about doing this, the way that they go about adding this financial news data is they use a model called Stoch-Tuveck model. I'm sure many of you are familiar with the word Tuveck model. It's the same idea. So what the Stoch-Tuveck model does then is it's taking in a vector, so a word vector, and this word vector will then be representing any news articles that we have. And then from this word vector, from this news article, this word vector will then represent or produce a numerical vector. And then once we have this numerical vector that's capturing this semantic meaning that we get from this news, we can then use that numerical vector also with our input in order to model this predicting stock market movements. And how they combine the two different streams of data is they use this two-stream gate recurrent unit. And then that's how they combine the two streams of data. So they combine it and it processes these two streams in parallel. And then from there, it will learn these two different patterns from both data sets that we have now, from the news side and from the historical side. And then over here they use LSTM. So they use long short-term memory networks instead of recurrent neural networks. And let's see what the reasoning behind that is. So when we look at recurrent neural networks, such as this one over here, what a recurrent neural network does that's a little bit different from an average neural network is it's able to look and capture information from previous steps in our sequence. So as you can see, it's capturing that previous step in the sequence and it's able to do that. But what they look at here is they decide to use this LSTM instead of a deep neural network and instead of a recurrent neural network. And the one reason is because the LSTM has been designed for specifically to deal with time series data. So that's why they use the LSTM instead of a neural network. And the reason why they use the LSTM instead of a recurrent neural network is the fact that a recurrent neural network specifically faces a challenge, and the challenge is called the vanishing gradient problem. And that the LSTM fixes this gradient issue. And what it is this LSTM can then remember longer sequences, and whereas recurrent neural network can't and isn't able to retain a long history of information, whereas LSTM is able to retain this long history of information. But it is interesting to note, so LSTM in practice has been used instead of recurrent neural network because of this vanishing gradient problem. But recently, many people have gone back to the recurrent neural network. And the reason for this is because people are using the recurrent neural network in conjunction with an attention mechanism. And when they use this attention mechanism with a recurrent neural network, it's fixing the problems, the vanishing gradient problem that we did find in the recurrent neural network. Okay, so when we look at another LSTM ensemble, is they use this LSTM that we just solved. They use an ensemble model, and they also use it with roots, mean squared, propagation optimization. And the main focus in the specific article that looked at the combination between LSTM and RMS prop is what they wanted to do is they wanted to predict intraday directional movement. So they wanted to look at the up or the down movements of stock prices, as we could see in this visual. And from the ensemble approach that they used with LSTM, they then use this RMS prop. And what it's doing is it's just updating your parameters from your LSTM during training. And then at the end of the day, it will predict whether your stock movements will move up or down. And then the last deep neural network combination is that of our convolutional neural network. So what convolutional neural networks doing specifically is the main task is therefore image recognition that we're all very familiar with. And why this is so interesting that they use this is this convolutional neural network. It can look at market dynamics from both the visual cues as well as our normal time-based cues that we usually use. And it's able to incorporate then these visual cues as well as our time-based data that we use. So it's using cues from both sets in order to then get to the best prediction at the end of the day. So now that we've seen how to integrate, all these variety of different techniques in machine learning algorithms and how they added these techniques to get the best results out of it, what is the common goal and the common theme that we've seen throughout all of these different techniques? So one of the common goals was that of parameter tuning. So we saw that with that teaching learning-based optimization and how that dealt where we had better solutions that would then share that knowledge to our other solutions. And we also saw that our integration of multiple data sources was very important. So we specifically saw that when they added the news data using that stock-to-vec model in our deep neural network. And then we also saw how it's very important to model how we can interpret our model. And we saw that with our glare and our SHAP, and how glare and SHAP helps us in general to see how the neural network made certain decisions and got to the specific prediction that it made. And we also saw how fuzzy theory has to deal with that uncertain and incomplete data. And one of the techniques there with the fuzzy theory was using gray theory. And then lastly, we saw how important it was to extract the best features before we carry on with our machine learning algorithm. So one example there was they used independent component analysis, and then that helped to extract those features. And another example was of that particle swarm optimization. And then once they extracted the features from there, they used the support vector machine from there. So we had a look at all these different machine learning algorithms. We saw what happens when different techniques get applied and how to get the best out of our stock returns from there. So thank you for joining our reading group talk today. I hope that it was a good overview of the different machine learning techniques that there is available out there. I hope that these different techniques sparked some interest for further research to see a bit more in depth of that. And I also hope that this overview will help you with any of your future projects that you have in mind.